Okay, let's get going. So firstly, thank you all for pulling yourself away from lunch to come back to the conference. So yeah, we're going to be talking about Enigma today. Bit of a history lesson, and then some minimal code at the end as well. We can't do a talk without having some F# in any of my presentations. So just a bit about me first. So who am I? My name's Isaac Abraham. I'm the author of F# in Action. I've been working in .NET and Azure for many years now. I think I started on C# 1.0, so Visual Studio 7. So if any of you remember, anyone remember Visual Studio 7? Like early days, you know what I'm talking about. The good old days of .NET. And yeah, I'm a tech entrepreneur today, so I build consultancies and support existing organizations growing and scaling. So I guess the first thing is, why did I want to talk about Enigma today? This is something I actually did a talk on years and years ago. And then probably a year ago, I thought, let's actually bring it back again. It's probably a good time to do so. I think firstly, history and like World War II has always been a kind of a pet hobby of mine. I've always sort of had some interest in it and read up on it a bit, but I thought also with like today's world of AI and sort of developments in computer science, this would be an interesting thing to talk about, and just to see how things from 75 years ago, 80 years ago, are still in some ways relevant today, and what the parallels that we can draw. And also just in terms of modeling problems, like how can we model a system in a programming language, and the fact that it actually really suits itself very well to functional programming was something I thought was quite interesting and fun to do. So the agenda for today, we'll stick to an hour. I could probably go on for double that, but I'll try my best to stay to the hour. Firstly, just overview of what the Enigma machine is, some context about where it came from, maybe dispel some myths about what we think we know about it, and then actually a bit of a deeper dive into how the machine works, what it really does, and then the last part of the talk will be about actually modeling it in code, how we might test it, how it was broken, things like this. So the Enigma machine, at its most basic, is an encryption device and decryption device. It basically took plain text and converted it into ciphertext. So you can think of it as just a mechanical password system. It was essentially almost like a typewriter in some ways. So you had this keyboard on the top, you'd press a key, and then it would go through a series of mechanisms and come back with a set of lights on the top that would then say, if you pressed A, it's actually being encoded into G, for example. At the time when this came out, it was like cutting edge. No one had done something quite like this before. One of the key things about it was that unlike other substitution matrices and encryption systems, this was what we called a polyalphabetic system. So here you type in like attack at dawn, go through the Enigma, and you'd get back different letters at the other end. The interesting thing is here, unlike with other encryption devices at the time, if you see there we've got like TT in attack, but on the right-hand side it's X and F. So it doesn't give back the same letter both times. And that was a really important thing. Another thing that was really good about the Enigma at the time, or thought to be, was that it could encrypt and decrypt. So once you'd configured the machine a certain way, you put in text, you got your ciphertext out, but someone else could put the ciphertext in, and they would get back the original plain text. So it worked both ways. So the core components, really, we've got this keyboard, which is where you type in the message. And then at the front of it, you've got this thing called a plugboard. And the plugboard essentially was a substitution. So you'd wire up literally like the letter A to S and T to V. And that would be like the first set of substitutions. And then you had these three rotors, which were again mappings from one letter to another, and it would push through all of them. And then you had this thing called a reflector at the very back, which did the same thing, another set of substitutions, and then you had this lamp board, which was, again, lighting up keys to say, you pressed A, it's gone through all these different layers, and it's come back with T or something. We'll go through each of the components in a bit more detail afterwards, but that's at a high level what it is. Press a key, go through a set of rotors and mechanisms, and then light up what the output is. What made it so powerful at the time was it automatically changed the encryption sequence after each key press. So you'd press a key, and then the rotors would shift, so you'd get a different encryption set of encryption keys, essentially, on the second key press, and the third and the fourth. So even if you knew the initial one, you had to know the sequence in which it would change to in order to decrypt a message. We already touched on the fact that it's symmetric, so input, output, but you could put the output in and get the original input back as well. And thirdly, it was just a huge number of combinations. There was actually 159 quintillion combinations. So I'll show you how many zeros it is, but it goes off the edge of the screen, sort of thing. But this was really a breakthrough because it meant the Germans felt that they were confident that they could send any number of messages over radio waves, but no one could actually decrypt them unless you had this device, basically. Important to understand that the Enigma was not developed by the Nazis. A lot of people seem to think it was developed by the Nazis in World War II, but it was actually a commercial device about 20 years earlier that was developed for government, banks, those sorts of companies that really wanted to encrypt key messages, but it wasn't designed originally for the military. Then the German Navy saw it, they decided they wanted to adopt it, and then they started making some enhancements to it to make it more secure. So, for example, the commercial version had only 3 rotors. When the Navy took it, they wanted to make 5 rotors, so instead of only 3 levels of encryption, you had 5. And they also added this plugboard as well. So the plugboard was this set of translations at the front, and that actually made it a huge amount more secure. So the original device had like the fundamentals in place, and then the military took it and they made it somewhat more secure. Right. Okay. So to get the scale of the use in World War II, and when you look at these numbers today, it doesn't really feel like much. So 40,000 machines were in operation at any one time, and maybe 200,000 messages being encrypted, decrypted every day. Now, if we think about that, look at some website like Amazon, that's probably the amount of messages they do in half a second, sort of thing. But in those days, that was like a quantum leap forward, because you could just do near real-time communication between different units, different divisions, and not have to worry about anyone else understanding what you're saying. So this was a real leap forward. And you had 3 different branches using it, but also you had it over different continents. So, it was essentially a worldwide encryption system that the Germans were using. That's how many messages, how many combinations there are. So when I said 159 quintillion, that's a lot of zeros. It was so large that the Germans thought it would take millions of years to brute force this, which was true at the time. But this kind of confidence also led to what we'll look at later, which is how the Allies were able to break the machine and how they could essentially decrypt the messages, because the Germans simply thought, this number is so large, it's impossible to break. The fact is, though, I don't know if anyone's ever been to Bletchley Park in the UK. Has anyone visited? Okay, great. So this was basically the secret sort of building in the countryside in the UK during World War II, where it was basically under the cover set up as just a code-breaking facility. If anyone's seen the film Imitation Game with Benedict Cumberbatch, so that's actually shot in this building. And it's a museum today. If you're ever in the UK and you've got half a day to kill, I'd really recommend going there. You can literally see where the code breakers worked, go in the huts and so on. It's really impressive. It was so secret that many people that worked there, they basically didn't tell anyone what they were doing. So some of them were actually ostracized by family and friends because they thought, you're not doing your thing for king and country, we're fighting a world war for our survival, you're not doing anything. And many of them went to their graves not actually telling their families what they did. And it was only years later when things were declassified that they realized, my child or my grandparents or whatever were actually doing this really key, important thing, but no one actually knew about it. So what I'd like to look at is like how the Enigma actually worked next, and then how it was able to be broken, essentially. So I touched on this before, but just to belabor the point a little. So a monoalphabetic substitution matrix is essentially one where the same letter will always give back the same letter. And polyalphabetic is one where you'll get back different letters depending on the order. So you can see, for example, on the middle right example there, we've got this ABA, and you can see it gives back ZCF. And that's the same as the first one for the two A's, because they're in the same position, but the middle letter obviously is different. Okay. So I'm just going to look at the different components now. So this is essentially what a rotor looked like. So those are 3 rotors there. And essentially they're just cogs with a number on each part. And that's essentially how many letters we're going to shift by. So if we've got the letter A and it was at the first position, it would translate it to a B. If it was at the 5th position, it would translate it to an F, for example. And then that would go through the next one and the next one. So you had 3 translations before you got to the very end. Then it would go through this thing called a reflector, which we'll talk about in a minute. But essentially, you had these 3 rotors. Now, the key thing was that on each key press, the first rotor would move 1 notch. And after you'd gone through 26 times, the middle notch would then turn once. And then when you'd gone through that one 26 times, the last one would turn 1 notch. So each time it changed, it basically gave a different cipher. And then at the end of that, you had this thing called a reflector, which essentially inverted the signal, so it went back through the original 3 wheels. So you went 1, 2, 3, reflect, 3, 2, 1. So instead of just having 3 sets of translations, you had 6, plus the reflector, which itself was also a translation. So you had 7 stages from these 4 components. This also meant that you had this symmetrical input-output. So once you'd gone in, you could also send the same message back out and get the original input back in through this reflector. That was really convenient because you didn't need 2 machines. You could just take one Enigma machine and use it for both sending and receiving messages, which was good. But the problem was that was also a mathematical flaw with the system that meant that the Allies could actually crack the Enigma a bit more easily. And the final thing was this plugboard. So I touched on this before. And you can see literally you've got wires that go from one letter to another. So it's literally the operators would put these wires in. And you didn't have to do all 26 letters. You could do none or 1 or 2. But it was just an optional extra stage of translations. Without this, the Enigma would have been much, much easier to break. It added millions and millions of possibilities on top of it. So if you think of it like a signal chain, let's see if this works. Oh, no, it doesn't. Okay. So you can sort of follow this line. If you imagine you've got the plugboard on the left and you start with the letter C, you can sort of follow the line across that would go through C to B, and then B to E, and then E to B again, and then B to F, and so on. And you can follow the line through. But you can think of this as just a pipeline of different components that are doing one mapping after another, connect them all together, and you end up with some letter at the end. It's actually not especially complicated when you break each of these things down into just a character translation. If that was all there was to it, though, and the Allies actually had one of these machines, then it would have been fairly easy to break because you've got the machine, that's it. So you essentially had different configurations, so different rotors, different starting positions, different plugboard settings that the Nazis would distribute to the entire army for a month at a time or so. So this is an example of a book where every day it's saying what the configuration settings are. So they'd start the day, wire up the machine to these settings, knowing that the listeners, the receivers, had also done this. And obviously this book was top secret. The Allies occasionally did capture one, and then they would have a month of codes. But then the Nazis would sometimes reissue them, or after that time, then there was nothing that they could do. Also, interestingly, the Nazis came up with what they thought was a very ingenious thing to make it even more secure, which was the operator at the very start of the message using this would pick 6 letters, which was 3 and 3 letters repeated twice, which was their custom key just for that message. And then the receiver at the other end would use those 3 letters to then configure the machine based on those 3 characters. So it might just be move each rotor forward by a certain number of positions. Then They thought this was a really good thing to do because it meant that even with this book, you still needed to know the extra 3 characters, but it actually ended up being a hindrance to the Nazis, and it made it easier for the Allies to actually break the Enigma. Okay. So I'm just going to show a very quick demo of a little app I created. Let's move out of that. At some point today, I'm going to forget that I'm still running PowerPoint and start coding and stuff. You guys are going to have to shout at me and say, like, can't see anything. Right. But you can see that now. So this is, I'm not sure how clear that is, if it's all right. Or, yeah. This is basically an app, a web app I've written, ironically, in F#. I'm just going to do my 1 minute of sort of sales. This is a React JavaScript app on the front end, but it's actually entirely written in F#. It's all transpiled into JavaScript and React. And what this does is simulate the real Enigma machine. So you can see we've got like rotors 3, 2, 1, then a reflector, and then rotors 1, 2, and 3. I'll just try and make it a bit bigger. Yeah, there we go. So if I type in, for example, I don't know, Isaac, because I'm super imaginative, then you'll see we've got this encrypted text out, and I'll just focus on this for a second. But what I can also do is put that in, and with the same configuration, you'll see that I get the original message. So that's essentially showing that you've got this symmetrical way of working. And what I can do is, if I really want, I can sort of follow the flow of messages. So if I just scroll down a little bit here, and put in the letter C, and then zoom in, you'll see that I can see like C goes to K, and then I can go to the second rotor and see K goes to L, and so on and so forth. I'm also just going to restart this. And what I'm just going to do is show you that as I'm pressing A, you'll see that the left rotor is kind of shifting along. That's simulating the notches moving. And then when I've done it a certain number of times, you'll see rotor 2 has now moved as well. So that's simulating going a whole circuit on rotor 1, which has now moved rotor 2. And if I keep typing letters, you'll see that rotor 2 starts to move as well. And then eventually rotor 3 will move. Okay, let's go back to Mr. PowerPoint. And that's all online, so if you really want to see this code, you're more than welcome to. Let's just talk now about how we actually did break it, though. So we've got this machine that's basically sending hundreds of thousands of messages. The Allies have got 1 or 2 of these machines, but then it's like, what do we do with it? How do we figure it out? So they actually had a huge helping hand by 3 Polish mathematicians before the war started. So if you remember, I said that the Enigma was a commercial device and the Nazis were using it from like the late 1920s, so a good 10 years before the war started. These mathematicians could see what was happening. They actually were able to reverse engineer the initial versions of the Enigma machine without actually having one. So by 1938, just when the war was about to start, they basically created a machine, a very crude machine that could actually reverse engineer what the keys are given some messages. The problem is that the war started, and obviously these Polish mathematicians couldn't do their work anymore. What they did do, though, was give the British and the French everything that they'd learned. So that sort of fast-forwarded and accelerated the British efforts to break the Enigma machine and try and figure out how to work with it. Okay, so back to Bletchley Park. I'll just give you a little bit of insight into that. At its peak, there were over 10,000 people working here, all in sort of complete secrecy. Interestingly, about 3/4 of them were women, partly because many of the men were off at war in actually units. They had different huts, which specialized in different types of machines and types of messages. So one were focusing on the Navy, some on the Army, and so on and so forth. It ran 24/7, so you had 3 shifts of 8 hours, and then they would go off and another shift would come on. But that's how like work intensive it was to try and crack these messages. And all of the existing kind of techniques that mathematicians had, things like frequency analysis, just didn't work with the Enigma machine. So frequency analysis was where you would sort of see, oh, this letter is appearing many, many times. It might be a really popular letter in the English language or the German language. And if a letter appears very few times, it's probably, X or W or something. But that didn't work because of this polyalphabetic encryption system. Okay. Let's carry on. I'm just going to touch on Alan Turing here. So again, if you've seen the film, you'll know about him. But in short, he was this incredible mathematician, and in some ways the father of computer science, one of the foremost people in the 20th century that really had this idea of a computer. So he created these papers. In 1936, he had this paper introducing this idea of the Turing machine, and essentially a thinking computer. At Bletchley Park, he worked on the naval messages, which was considered to be the hardest of the three different types of messages. The Navy had more wheels, they had more processes and procedures. And he basically created this thing called the Turing Bombe, which was this large machine. And if you go to the Bletchley Park, you can actually see one of them that they've recreated and actually see it working. But it's this huge mechanical machine that basically goes through and brute forces, in a sense, all the combinations that the Enigma would come up with. I think it's worth talking a little bit just about artificial intelligence at this point. And obviously, we're all using things like ChatGPT and Anthropic and Gemini and so on. Alan Turing had this idea of this thing called the Turing test. And for those of you that aren't sure, like AIs today, although they don't think in the sense that we do, it's really, from what I understand it, mostly pattern recognition and prediction. I think we're fairly confident that it would pass the Turing test today, which was essentially you'd have this operator who's person C, and they'd be behind a wall with two people or two responders. One is a computer, one's a real person, and they would have a conversation with both of them. And if they can't tell which one is the man and which one is the machine, or which one's the woman in the machine, then the computer has passed the Turing test. Yeah, and I think it's not controversial to say today, if you are chatting with someone at the other end and it's an AI, you probably wouldn't know for quite a while. Maybe if there's EM dashes in the response, then you'll know it's from ChatGPT. But if it's not that, then it's very difficult to know. I actually did have a supplier of mine email me the other day with I asked them a question, they came up with this huge message, and I was like, that's a really detailed, well thought out response. And then I just saw EM dashes everywhere, and I was like, he's just gone into ChatGPT, asked the question, and pasted the response in. But that was one of the giveaways, and the fact that it was really, really friendly and polite. So that's a picture of the Bombe. So it's this huge mechanical machine, and it would basically, you'd give it some settings, and what's important, you'd also give it what was called a crib. So imagine you've got this long message in encrypted German. What you would do with the bomb is say, I know that the first 5 letters are this. Make the assumption that the first 5 letters are going to be this, and when you find any combination that would give rise to those first 5 letters, stop. And I will use that configuration on the rest of the message and see if it really is something. They built 200 of these machines running 24/7. And so you would essentially go through some messages, try it, get one combination, and then hopefully you had a key for the rest of the day. And then you could decrypt all the messages and then try it again the next day. There are, I think, 2 sides to how Enigma was able to be broken. One is the mathematical side. So firstly, you can't encrypt to yourself. So if you put in the letter A, you will never get the letter A back out again. So immediately, you've reduced the search space there of permutations, especially if it's across an entirely long message. And the symmetrical nature of A goes to B, B goes back to A, let the mathematicians create patterns that again enable them to cut down the search space. But I think that wouldn't have been enough. The truth is, it was more about the human side of the operators that led to how the Allies were able to break Enigma. And in any form of security, I think we've seen this in the past where people, work in some hyper-secure environment and then they put all the data on the USB stick and then leave it on the tube. And it's like, what was the point of all these processes? This human has just destroyed everything we've built. So one thing with things like every message at the start of the day, there was always a weather report, and it was normally structured in exactly the same way. So the allies could make a guess that, oh, I've received this message. It looks like a weather report. Let's assume the first words are weather report. Things like nothing to report, which was a very common message sent from one army unit to another, or things like Heil Hitler. And that's the example they give in the film, but it really was. A lot of messages would be signed off with that. So if you knew that, you could say the last few letters are going to look like this, and then the bomber could then know when it's probably received a good message. I also touched on before that the operators would send these 3 letters at the start, or 6 letters at the start. The problem was they often used the same 6 letters every day. And that could be, and it really was often their girlfriend's name or a swear word or just hello or something like this. Once the Allies realized this, again, that was another key to reverse engineering essentially what the cipher was that day. Once they'd done this, they were able to break like 90,000 messages a month. It's predicted that it was like shortened the war by 2 to 4 years. Right up until the end, the Germans had suspected, from what I understand, that the Allies might have some success, but they had no idea how comprehensive this was and how easily they were able to break messages after they'd figured this out. Or that they'd developed their own technology to essentially reverse and brute force through the keys. Okay, right. Now's where the fun starts. Now we dive into some code. So let's jump over here. So what I want to do is really 3 things. First thing is that font too small? Yes? Right. Let's keep going. Yeah, that's better. When I get the thumbs up, then I know. So I assume many people who are .NET developers, C# people, yeah? Is there anyone who's done any F# before? Oh, wow. Probably more in this room than in any other room at the moment in the world. There's only 12 of us, right, worldwide, so that's it. So for those of you who don't know, F# is a statically typed language that runs on .NET. It's been part of Visual Studio since like 2010, so .NET 4. It's mature, performant, and to be honest, in my opinion, pretty simple. I used C# for like 10 to 15 years before I transitioned over to F#. I never really looked back. We're going to see only a fairly simple part of F# today. It's not about F# really, but more about the modeling side. But what I'm going to do first is really just show you an example of how you can build an encryption system that works in a similar way to what Enigma did, just with a couple of simple functions. So what I've got here is Visual Studio Code. One of the nice things that F# has is this thing called a REPL. So anyone who's worked in Python or R will know what this is. If you don't, it's kind of like the immediate window in C#, but instead of on a running application, it's just, I can open up some code and just execute arbitrary bits of it and then create some state and start working with it. So let's just reset this, actually. And then, yeah, that's how we roll. Good. Okay, so at the bottom here, you're going to see some output, which is, it looks really simple, but it's essentially the code that I've written at the top, and I'm sending it into the REPL, into the running sort of system. So I have a function here called forward1. And this function here is going to take in some character called C, and I'm just going to do some very simple permutation to it. I'm going to convert it to upper text, and then I'm going to do some offset to basically move it forward 1 character. I got ChatGPT to write that code, this offset stuff. But it basically will just let me send in a character, and it will move it forward 1. And if it gets to Z, it will wrap it round to A. So I'm just going to compile that, and then I'm going to just test it. So I'm going to say forward 1, and I'll put in the letter A. And then if I look at the bottom of the screen, you'll see I've got chart equals B. So I can just create a function, call it, and just experiment with it. And then I've got another function called back2, which does the same thing as the other one, except it's going backwards 2 letters. So again, I'm going to just send that to the REPL, and then I can just test that out. So if I've done D, I get back B at the bottom. It's going back 2. If I wanted to, I could compose these two functions together. So I could say I want a function that's going to move forward 1 letter and then go back 2. So you can think of that as like the rotors. I've got one rotor that's doing one transformation and then another one that's going to do another. And if we were using C#, it might look something like this, where we put parentheses around the inner function, and then you wrap the result into another function call. In F#, we don't need to do that. We have this thing called a pipeline, which is that pipe and an arrow, and that's saying take the output of the first expression and pipe that into the function on the right-hand side. So you can make these nice sort of pipes where I could say go forward 1, and then go forward 1 again, and then go back 2, sort of thing. Yeah, and very, very simple, but it looks quite readable. And we can even go a bit further, and we could use a slightly simpler syntax, which is this double arrow. And what essentially that's saying is take the function on the left, plug it into the function on the right, compose them into one, and give me back a new function that does the sum of those two. It's almost like plussing 2 delegates together, in a way. So you sum 2 functions into one, you get back a new one. So I could create an Enigma machine just with these functions if I really wanted to. So that could be, rotor 1 goes to rotor 2, goes to rotor 3, goes to reflector. It's just plugging some simple functions together. Let's jump back quickly into some code. So before I go too much further, I just want to say, F# and functional programming, before I get any further, everyone always talks about it as about maths and science. And, use F# for hard problems, use functional programming for hard problems, but for everything else that's real world, use OO. I never saw it that way. I saw initially F# and FP as you can solve hard problems with simple code. But today I just think of it as you can solve simple problems with really simple code. It's it doesn't have to be a zero-sum game. It doesn't have to be that F# or FP is only for a certain category of problems. It's general purpose programming, just with a different, scale or different slant on how you do different things. And to be fair, we see that today, I think, with many programming languages. I think most of the features in C# today, in the last few releases, have been basically taken heavily from the functional side of things. I saw a talk on Java. The next version of Java, it will have essentially higher kinds or features like that is taken from Scala. I think we're seeing a lot of this kind of cross-pollination across languages. Although you can do many of these things in F#, you won't see any of them today. So you won't really see me creating classes or objects. You don't need inheritance. You don't need polymorphism, DI, none of those things. You won't see any hierarchies like this with animals going to birds, going to chickens. I remember studying when I did my degree at uni, and it wasn't a computer science degree. It wasn't like hardcore maths. It was very much about writing software. But I remember looking at this and being super excited about using this in the real world when I started actual work. And I must have missed my calling because I never actually ever developed this kind of class hierarchy. Maybe if I'd have worked at a vet's or animal hospital, it might have been more useful. But I never saw this. I put this together actually just very quickly, just what would it look like if I was to try and model the Enigma machine using classical OO concepts? And I'd probably have something that I call, a machine or Enigma as my sort of top-level class. And it might have some methods on it like translate and reset the state to go back to the beginning. And it might have some private fields on it, like a rotor. And that might have some messages on it, or methods like rotate and translate and a reflector and so on. I didn't really want to get into any of that when I was doing this, though. In F#, it's much more common to just break things into 3 simple sort of categories of like functions, simple types, and values that hold data. We don't really think of things in terms of classes. It's more about data, which have some static shape, which you would consider records in C# today, and just some functions that take in some data and give you back other data. It's very, very simple in this regard. So if you think about what we looked at before with the signal chain, we can actually model that as different types and different functions. There's clearly 5 components here. We've got a plugboard, we've got 3 rotors, and a reflector. And each of them are kind of piped together or chained together. You could think of this again, if you're a C# person, as like a fluent interface style API. You know, plugboard.translate, .rotor1.translate, and so on. But if you look at them, you realize that they all actually do the same thing. They all have the same signature. They all take in a character, and they all give back another character. They don't do anything else. Yeah, the reflector takes in one character, gives back another, which is passed on to the rotors, and so on and so forth. And in a functional language, we would model that like this. This is the signature of that behavior. It's just char goes to char. And we can literally model that exact same signal path as just a pipeline of functions. So we've got a plugboard function and a rotor function and another rotor function, and each of them is just getting some data and threading it through this chain. And using that exact same syntax that I showed you before, we can do exactly that now in this Enigma world. I could say I've got a plugboard function, and I'm plugging that together with a rotor function and another rotor function and a reflector, and all the way back out. And this is literally, you'll see in a minute, that's exactly the code that I have in the simulation I've built. You'd also have to think about the state changes. So if you think with what I told you before, that each wheel is changing position, with functional programming, you don't really have mutable state, you have immutable state. So what you would typically do is define a type that has the exact state in it of the whole world. So what I've got here is like rotor 1 position, rotor 2, what direction am I going in? Am I going to the reflector or back out? And that's all you need, is a very simple record type that models the state, and you pass that in for the ride along your chain. In any of the functional languages, you'll typically see this kind of syntax. So it would be not just a character to a character, but a character and some state. So the configuration in our case. So I want to translate the letter A, and the current state of my Enigma machine is this. Please give me back the next character. Right, so let's flip back again. And I'm just going to show you a little bit of what the actual code looks like. So let's get rid of that, and let's go up to the top. OK. So all I've literally got here are a few type definitions. So I've got the idea of a plugboard. And a plugboard is just a map, which is like a dictionary of character to character. So that would be the wires, essentially, that go from one letter to another. I have a direction called up and down, which is up to the reflector or back down again on the way out. And I've just defined some very simple functions. Move a letter forward. My alphabet is the letters A to Z, and I can actually execute this and see what it looks like, just if I want to explore my functions and what my behavior is. And then you can literally see, like, what is a rotor? Well, actually, it has an ID on it, which was just like rotor 1, rotor 2, rotor 6, rotor 7. It's got a mapping. It has an offset, which is the position it's currently at. And the overall machine, like the actual Enigma, well, again, there's not too much in there. It has 3 rotors, a reflector, a plugboard, and you can ignore this debug boolean. But really, that's all it is. It's just 5 different fields on a record that have some types with some data on them. There's nothing too complicated there. And literally, that is there, the entire kind of Enigma pipeline. It's like, I want to translate a letter on the plugboard, and then push it into the right rotor, then into the middle rotor, then into the left rotor, then I want to push it into the reflector, and then back out. So we literally have the exact same chain of messaging that we saw before, just in some code. That to me is like, once you understand the syntax here, which really isn't that hard, it takes like, I'd say half a day to get used to it, this matches really, really nicely to what we talked about before. Right. I'm just going to show you some examples of what this looks like. So let's just exit there. So what I've got here is an Enigma machine that I'm making. And I've said I want to start with a default Enigma machine with 3 specific rotors, rotors 3, 6, and 8. So these were actually like rotor 3. There were like 8 rotors in that the Nazis used. So these are physical wheels that they'd sent to every single unit. And at the start of the day, it would be like the right rotor is rotor 3, the middle rotor is rotor 6, and the left rotor is rotor 1, or something like this. So they were actually like named rotors, as it were. So I'm just sort of creating a machine with some configuration, and then I can actually translate a message. So I could say, translate this message, and for those of you who can speak German, I'll just zoom in a little bit more. Let's move over there. Come on, chance. Let's do that again. There we go. There we go. So if you can read German, you can sort of see at the bottom there, you have this huge bit of text. The Germans would use like certain combinations, so they would use like the letter Q instead of CH to save on time, and they'd use Z as a space and X as a full stop. But you can sort of see words like Zwo, which is 2, and then Fahrt, which is drive, and so on and so forth. And these are actual real messages that the Nazis sent. You can go online and see a whole set of real decrypted messages. And that was actually how I tested this, was I took real messages, piped it through, and like, can I figure out what it's really saying, and so on. And like Standort, which is like position, and so on and so forth. And I'll just leave that as it is. Let's try this one. Yeah, okay, let's not bother with that. I did create like, try to simulate a Bombe machine as well. So let's just take this. So here's some encrypted text that I've got, which is that top red text. And I've basically said, well, I don't know what the settings are. Let's see if I can brute force my way to actually finding the configuration. And it literally just goes through every configuration and sees if it can find a match. And just like the real thing, I basically have to give it the first few words of what I think the real plain text is, and then it will just continue going through until it matches that plain text. And once it does, it will give me back the configuration, and then I can try that on the real thing. So I'm just going to run that through, and hopefully it won't take too long. It takes around 20 seconds or so to go through like a few million combinations. And then once we've got this back, I can try that against a machine with that configuration and see if it actually works. So you can see there it's run like 27,000 combinations, and then it's come back with a configuration. And then I can run it through, and you'll see there we've got this message, Tottenham Hotspur are the greatest team the world has ever seen. But I only knew the first few words. So anyway, right. Let's jump back here. We've still got like 15 minutes, which is good. I want to just talk a few of the benefits and then talk about testing and how you can prove whether your machine works, because that was actually quite an interesting thing. So firstly, I think we've got this natural expression of data transformations. So essentially, come on, yeah, there we go. Okay, sorry about that. We've got this real-world thing of different components, and we can model that in F# pretty accurately, like literally the same words in the same pipeline. And we can test each of these in isolation. Like I can literally take one of those functions and just test it out, and then I can plug it together with a few other functions and try that out. But I don't have to like run a web app, log in, do all these different things in order to test one little thing. I can just take that snippet of code in the REPL, compile it, and then test it out with different values. I didn't really touch too much on this, but this immutable state management is really valuable, because what it essentially means is instead of having to run through a whole series of transformations to get the machine into a certain state, I can just create some state and pass it into these pure static functions and just say, here's some state, here's a character, what should I get back? The end. It's very, very simple and easy to test with this. So I've kind of just started touching on this already. So for like testing, you could look at conventional unit testing. So we could say, here are some components, here are some scenarios I want to test out. Pretty easy. I could test rotors in isolation. I also touched on I could take some real-world historical messages and just prove that what they're giving me back is what the real outputs were. And that would be more of an integration test where I'm really testing the whole configuration of the system. But I could also use this thing called property-based testing. Has anyone heard of PBTs? Okay. So for those of you that haven't, property-based testing is a different way of testing where you test behaviors of a system rather than inputs and outputs. So in the example of the Enigma machine, we touched on the fact that no letter ever came back the same letter. So it would be great if we could say, well, please give me 1,000 random messages. I'm going to encrypt and decrypt all of those 1,000 messages, and I'm going to prove that each letter in the decrypted message, or the encrypted message rather, is not the same as the equivalent plain text message, essentially. What a property-based testing framework will do is give you those 1,000 random messages. And it will do short words, long words, all sorts of different ones. You don't have to worry about coming up with those. And every time you run it, it will generate 1,000 new words. And we could also look at things like encrypting and then decrypting will always give back the input. And again, you don't really care then what the message is. Give me 1,000 different messages. I just want to prove that that behavior always holds true. If you're using F#, the .NET story is the same as any unit testing, so you can use things like XUnit and MS Test, and you'll get the green ticks and stuff in Visual Studio. There's also a testing library that was designed for F# called Expecto that I'll show you in a minute. And there's a library called FSCheck, which is a property-based testing. Both Expecto and FSCheck have C# wrappers. So if you're interested in property-based testing, you can also use this library in your C# apps today. So I'll just do a quick demo of that, and then I think we'll wrap up. So I'm not going to do too much here, but I'll just give you an example of some of the tests that I did. So this is like my first unit test, and the test was called should translate a message that only needs the right rotor to advance. So it's a fairly short message, but enough that it's long enough that the rotor will move forward once, but not the second rotor. And that should give back the message congratulations, for example. And then I had a whole bunch of these messages, of these tests. And then I went down to these Enigma tests, which were actual real messages that said, you know, this text here should map to this message here. And again, you can see some German here, like that's feindlicher, so like enemy infantry has arrived, blah, blah, blah. So there are some real messages there. And then the interesting one at the very end is this property-based testing stuff. So I've got here, encrypting and decrypting text always gives back the original text. And you'll see this strange bit of code here. It says fun text. So that's like a lambda, where some argument of text, which is a string, is going to be passed in. I'm not picking that text. But what I am doing is then translating that text and then translating it back again. And it should equal the input again. And it doesn't matter what the messages are, I'm going to get 1,000 different input strings, and as long as it always matches, then I'm fine. And I had a couple of other ones here as well. And then when I want to run all the tests, hopefully I can just click on that green tick, and then you'll see that all the tests on the right have run. And I get big green ticks, which means all is good with the world. Okay. Okay. Bit more poignant at this point. So the first thing I wanted to touch on was like what I consider the lost legacy, which was after 1945, the war's ended. The British have developed this amazing technology called the Bombe, and they've learned all these amazing lessons with Alan Turing's work and so on and so forth. What should we do with this amazing things? I know what we'll do. We will destroy every single Bombe and throw away every bit of information we learned during the war because we're worried about the Russians finding it because the Cold War is just about to start up. And that's exactly what the British did. We literally destroyed nearly everything that we learned and classified everything. And it was only 25 years later that we started talking about it. For the British government and society, this was really unfortunate because we essentially lost our position as the world leader in computer science at this point, and the Americans essentially didn't have the same approach. They used all those lessons and moved forward from there. Also, just a few words on Alan Turing. So after the World War finished, he stayed on at MPL to work on computer design and his plans to actually make a real computer. But within a few years, he was convicted for homosexuality. In Britain at that time, you had two options if you were found as a homosexual. Either A, go to prison, or B, chemical castration. Unfortunately, that's what he chose, and he killed himself just a few years after that. So eventually, the government and the royal family did apologize for what he did, for what they did to him, like 60 years later. Obviously, it's too little, too late. So I think that's really unfortunate, obviously, and a terrible outcome for someone who did so much for Britain. They did eventually pardon everyone who had been affected by this law for so many years. But I think it's a really unfortunate end and a really bad end to what should have been someone who really had done so much for the country and for ultimately the world. Just a few lessons for modern security. Although my specialty is not in cybersecurity and encryption, but things like no system is unbreakable if there are mathematical weaknesses in the system, and that human behavior and procedures will always, like, if they're not proper, you will always end up ruining all the hard work you've done from the operational and mechanical side. Security through obscurity is not enough. And I guess the best thing to do is to anticipate attacks and try and break your own systems, or get other people to try and break your systems rather than rely on waiting until someone has given you a ransomware attack, sort of thing. Tiny bit on functional programming takeaways. So domain modeling through types. I know we didn't spend too much time looking at it, but simple functions, simple records, and just data. You can get so far with that. You don't need inheritance, you don't need interfaces, you don't need frameworks. Pipelines as a way of modeling a signal chain. Immutable states rather than stateful mutable systems, much easier to test, much. And composition of simple components. You know, you build small things that do one thing really well, and then you plug them together to make much larger systems that appear very complicated, but actually you still have built them on very simple, easily testable components. Brilliant. So I think that's about it. Thank you very much. I think we're almost out of time. I will just send you a couple of links. So if you want to take a screenshot of that, you can find the exact repository on GitHub. You can hit me on X, Isaac_Abraham. I know not everyone uses X. I'm really sorry. I just don't have the time to do 7 different social media systems. So that's the only one I'm on. But please come chat to me afterwards. You can message me there or drop me an email. I'd love to talk to you and chat more about Enigma or F#. Thank you very much.